Welcome back, ladies and gentlemen. Here we are. We're going to be continuing with carrying capacity. The question, is there enough food for us? Are we going to run out of space? What's going to happen? Relax. I got you. So carrying capacity is that dotted line that you saw on the previous graphs. Carrying capacity is the maximum number of individuals that can be supported forever by an ecosystem. Doesn't mean you can't get more individuals, but you won't be able to support them. That sounds bad. And we're already at how many? Almost 8 billion, 7.8 billion people? That sounds like a lot. Oh, maybe we're in trouble? Let's take a look. The population will still vary over time with the seasons and resources, but for the most part, the organism will reach that dynamic equilibrium and stay there. So what we're seeing here, right, is that the blue line is the carrying capacity. The sort of purple line here is going up and down, fluctuating. Why? Well, because, like in spring, they have lots of babies, and then in winter, some of the old ones die, and maybe one year they have less, but it wiggles. This is what I mean by a dynamic equilibrium. It's wiggling around that same line. Okay. So we've got the definition of carrying capacity, but what does that mean for people? Come on, Mr. C, that's what we want to know. Once the carrying capacity is reached, the population size will increase and decrease around that limit. All right, pretty straightforward. Drawing a line through the middle of these fluctuations, fancy way to say changes, represents the carrying capacity of that species. Now, why does this line exist? Well, there are three factors that determine the carrying capacity: resources, competition, and density. You can see here, this little chart here, right? So the number of fish is increasing, but then there's all these different factors that are contributing to pushing them down. Things like decreasing oxygen supply, low food supply, diseases, and other things. So there are things that are encouraging, or discouraging, I should say, discouraging the population growth. Okay, but let's take a look at these in more detail. Resources. Populations are limited by the amount of usable energy from the sun and or food, as well as the supply of water, carbon, nitrogen, and other essential elements. All that carbon cycle stuff we talked about. So here's some example. We got some abiotic resources like light, carbon, water, oxygen, nitrogen, shelter. And you got your biotic factors like food, diseases, and predators, right? Like if there's no food, well, then the population's not going to go up, right? If there's no oxygen, the population's not going to go up, right? Okay, seems pretty logical. So again, Mr. C, can we grow enough food for all the people? You said earlier that we need a lot of food. That sounds like a problem. Hold on, patience, patience. I know you're very excited. Patience. We're defining all the terms first. Competition. The existence of resources does not mean every creature gets access to them. Competition is both interspecific, different species, and intraspecific, same species, and it can limit the access to resources. So in this case here, we've got some vultures. Two vultures are fighting over the same kill. It's like, my kill, no, I want it. Here you got two different types of monkeys fighting over the same bananas. Okay? So this can happen between humans and other animals, or it can happen between humans, right? Like we've talked before about how hunters would deal with carnivores like wolves or bears or tigers that go after human livestock, cows and sheep and pigs, because we're like, whoa, that's our food. You don't get to eat it. So if we get any of this kind of competition here, humans tend to deal with it with a bit of a bang bang, or some other way, but usually it's the bang. Now, this competition between people, we get that too. To be honest, we don't get that nearly as much as we used to. I know that seems weird, but again, if we take a look at historically, the ancient Greeks, the ancient Romans, they lived in city-states with walls, and they'd fight each other constantly because you never knew when the neighbor was going to knock on your door and try to take all your stuff. Constant raiding and warfare was the norm. That's why you ended up with a citizen militia. At your age, you'd be getting ready to defend the city against anyone who would try to attack, because you never know when it was going to happen. We don't live in that kind of world anymore. Our world is a lot safer now, which is a nice thing, I gotta say. Finally, density. The more organisms there are in an environment, the more likely they have reached their carrying capacity. This is usually due to density, but there are some density independent factors as well. So density, right? Like, do you have like very few people, or are there lots of people? Now, each of these is going to affect things in a different way. There's a little more detail here, so we're going to go into it here. Density-dependent factors affect the population depending on its size. Dependent means that it depends on the size. So this can include competition, like we talked about, predation, aka predators eating you. It's easier for a wolf to find somebody if there's lots of them. Diseases, they spread really easily if there's lots of them. Food shortages and stress for being close to each other all act to decrease the size of the population by increasing the death rate and decreasing the birth rate. So some examples here is for the Gros Michel banana were all wiped out by a single type of disease, Panama fungus. Have you ever had banana flavored candy? And have you ever noticed that it doesn't really taste like a banana? Not really? Well, it does. It just doesn't taste like any banana that you've ever eaten because the banana that it tastes like doesn't exist anymore. The Gros Michel was the first type of mass cultivated banana that you could buy in the store, but they cultivated it everywhere. And it was a monoculture, meaning that it had one basic genetic variant. It was a clone, basically. So this was a problem because when a disease came around that could attack the Gros Michel, they had no protection, and it spread across the whole globe. It was wiped out, rendered extinct. It's gone. My parents ate Gros Michel bananas. They're gone. Now we have a new type of banana, and it was made exactly the same way. And the Panama fungus could come again and wipe it out again. Again, as we've discussed, ecosystems are fragile if there are very few organisms in them. And a farm with only one type of banana sounds pretty fragile. So competition, parasites, disease, predators, all of these are things that depend on the number of organisms, right? If there are more organisms, these things are more likely to happen. If there's less, these things are less likely to happen. Okay, that seems like most of the things, right? What's the other one? Density independent. It means that it doesn't matter how many organisms there are. These affect the population regardless of the density. Big or small, they'll be affected the same. These factors include things like natural disasters, forest fires, volcanoes, volcanic eruptions, floods, droughts, tornadoes, hurricanes, and human activity like deforestation also can act on things to change the population by increasing the death rate and decreasing the birth rate. So the eruption of Mount Vesuvius destroyed Pompeii back in ancient Roman times and the surrounding countryside. That wiped out the cities, that wiped out the farms, that wiped out the forests, it wiped out the countryside, it wiped out all sorts of things. Didn't matter what you were, when the mountain went kaboom, you were in trouble. Okay, so we got two big things here. You'll notice that humans are on the list as a density independent factor. We're kind of indiscriminate. Ooh. Here's another example of a density independent factor. The Chernobyl accident. You may have heard of this, you may not. The Chernobyl accident was a nuclear power plant located in what is modern day, I think, Ukraine, and it had a nuclear meltdown. That's bad. It was the single largest nuclear disaster that, wasn't a bomb on purpose. And the resulting city was evacuated. The explosion itself, right, the meltdown, you can see the damage it did here. Like, there it is. Pretty straightforward. But you'll notice that even the areas just around the nuclear power plant are totally fine. And here we've got like a building, and here's a picture of the building back during the time when it was filled with people, right? It's a color photograph. It wasn't that long ago. I think it was the 60s or 70s. I don't remember. I'll have to look it up. Either way, the building is just there, but the people are all gone. Most of them are gone. You can actually go visit Chernobyl now as a tourist. It's a completely empty city. All the amenities, bus stop, apartment buildings, schools, amusement parks, just abandoned, left where they were, reclaimed by the forest, as it were. Here's what a classroom looked like in 1997. Here's what it looked like in 2011. Nobody came in to trash it or anything. It's just decaying, falling apart. The things humans build, if we don't maintain them, they don't last. What's all this stuff on the top of the bookshelf? The wall. The wall has collapsed. All this debris. It was just left there. Again. This is a nursery school. There's just blocks and toys just left on the counter. Why? The red forest. So the reason why is because of what a nuclear disaster does. Nuclear reactions work through atomic fission, which is the splitting of atoms. We learned in chemistry that atoms are made of protons, neutrons, and electrons. And we learned stuff, for example, that helium has 2 protons. Hydrogen has 1 proton. So what's stopping me from taking a helium and cutting it into 2 hydrogens? I just cut it in half. Well, nothing's stopping you. except that it's really hard. But if you do, it releases a ton of energy. Now, originally we used this to make explosions, because humans. But then we figured out we could use it to make electricity. And the Chernobyl plant was one such place. The problem is that it releases so much energy that it also releases something called radiation. Now, radiation gets a bad rap. People just sort of assume and they think of how it looks in like a comic book or something, but radiation just means energy of some form. The problem is that that energy is very, very strong. And that energy interacts with living tissue in strange ways. It causes mutations. Now, unfortunately, becoming a mutant does not always mean you get special powers. You don't get eye lasers and healing factor. Becoming a mutant just means that there's a change to your genetic structure, which may or may not be a problem. Maybe it's completely benign, no effect whatsoever. Maybe it breaks down the machinery of your body so you can't survive. Maybe it gives you an advantage, but rolling the dice on that is not a good prospect. These trees here are red because the mutation from the radiation has done that. These trees are nowhere near the power plant, not even slightly. But that's the thing, they didn't have to be. The radiation spreads very, very far. Radiation effect can be pretty brutal. This is sort of measuring the strength of radiation, and what we see here is that, some things that you do. If you get 10, right here, 10 sieverts, it's called, of radiation in one dose, it's probably fatal within weeks. This, 6 sieverts, is the typical dose of the workers who were at the plant when the Chernobyl accident happened. They got 6. They died in a few months. 5 is a single dose needed to kill somebody, half of those people exposed within a month. 1 sievert is enough so you would get sick. You'd become nauseous. You wouldn't probably die, but you would end up having a real bad time. Here we go. The blast was in 1986. I had my numbers off. This number here is the exposure of people who were living in the city and had to be relocated, 0.1. 0.1 is the recommended limit for radiation workers every 5 years. If you work in a plant, don't be exposed more than that. A chest x-ray, way down here, 0.0001. It's way less than the natural radiation we're exposed to per year, 0.002. It's right there. Why is this important? Well, radiation does some pretty messy things to living tissue. And what you can see here is what effects it would have on you. Over here, you can see how much radiation there is kicking around the site of the explosion. The reactor core itself, 300 sieverts per hour. Remember, 10 means you die in a few weeks. Fragments of the fuel cells that cause the reaction, 150 to 200 per hour. The control room of the plant is 0.03 to 0.05 per hour. It's pretty dangerous. So why in the world am I bringing this up? Well, this is a natural disaster in the sense that it's a density independent, but it had a pretty big effect. There's Chernobyl, and there's the fallout of Chernobyl. This didn't just affect the city. The things humans do can have an impact across the whole globe. This one reaction left radioactive dust everywhere. Okay, now you're immediately panicking. But you just said that's lethal. Relax. Take another look at the chart. The amount that you get exposed to every year just through natural processes is 0.02. Sorry, 0.002. The explosion there dropped off pretty quick, right? Look, the nearby concrete mixing units near the power plant, 0.1. This spreading cloud of radioactive particles is not good, but it's not anything that's going to kill anybody. But it definitely shows the scope of the damage. So why do I bring this up? Because despite all of this, despite all of these problems, despite all of the dangers, the population of animals in the area around Chernobyl has increased compared to what it was before there was a city there. What? What does that mean? It means that a human city has a larger ecological impact as a density independent factor than a nuclear disaster. You saw in those pictures the overgrown bumper car. You saw the classroom falling apart. With humans gone, other animals can fill in to take the place. So even the natural disasters that are particularly bad leave opportunities. Now, don't get me wrong. As you saw, the trees were red. They were mutated. The deer and birds that live in this area are also mutated. They have their own problems. But they don't understand those problems. We do. That's why we avoid staying near that place. And we have made efforts to contain the reactor core. This is a giant concrete dome designed to protect the site of the initial reaction so nothing can get in there. It had to be built separately and then slowly lowered into place because nobody could survive working near the reactor core. All in an effort to contain the damage. Wow. So, if a population increases beyond a sustainable level, it produces conditions that will limit its further growth in numbers. For example, overcrowding will increase stress and promote the spread of disease or parasites, which cause an increased aggression and a neglect for offspring or children. This would lead to an increase in the death rate and a decrease in the birth rate, which causes the population to decrease. Okay. But Mr. C, I still have the same question. What about humans? Are we going to run out of stuff? I'll answer that next time. I know. Another cliffhanger. I'll see you then.